Now let's look at examples from the textbook. Example 20. The two circles, the bigger circle and the smaller circle. Now you can see that the smaller circle, the center is on the circumference of the bigger circle. And P is one of the intersections. Okay? And we need to prove that Pn is the tangent. Now, so far we have two ways to prove a line is a tangent. One is the converse of tangent perpendicular to radius, and the other one is the converse of angle in the alternate segment. We're going to use the first one. So first we need to join OP. Since ON is a diameter, maybe you specify in which circle. In circle M, I call it M. Therefore, angle OPN equal 90 degrees. Here I'm using a theorem that's called angle in the semicircle. I forgot to mention that in this part of the chapter, we follow strictly the deductive geometry now, which means the condition, conclusion, and the reference. Okay, so this is 90 degrees. And then my last argument, my second and the last argument, that is because OP is perpendicular to PN and OP is a radius. Therefore, PN is the tangent to the smaller circle at P. Now here I'm using the converse of tangent perpendicular to radius. And then I'm done. It's a simple proof, only 2 steps. But still, you must learn how to write a formal proof. The next example. In the figure, you can see a straight line and some equal angles. It's marked. These two are equal and these two are equal. Prove that A, B, D, E are concyclic. Now we have 3 tests for cyclic quadrilaterals. We have 3 tests. Now here I'm going to use test 3. Okay, I'm going to use test 3. I'm going to focus on this angle and this angle. And I'm going to prove they're equal angles. Okay, and it's actually not bad. It's not that bad. So first, in triangle CDE, that's this triangle, I have angle BDE equal angle BCD plus angle CBD. Exterior angle of triangle. Right? This one equal to this one plus this one. Okay? That's one thing. That's one thing. Now for convenience, I think it's easier if I use a letter to represent these equal angles. So I'm going to let angle ABE and angle CBD be X, and angle BCD and angle BDA be Y. So I have Y, X, x and y. Therefore, angle BDE, the exterior angle, equal x plus y. Okay. Now, since this together is x plus y, I know that angle ADE. Therefore, angle ADE plus angle ADB equal x plus y. And angle ADE must equal x. Okay? Now here what I did is just some substitution and replacement. But in the end, I get this is x and this is y. So this together equal x plus y. And now I have my final argument. That is, in triangle not in triangle. In the quadrilateral ABDE, angle ABE and angle ADE are both x. Therefore, A, B, D, and E are concyclic. Now here I use test 3. So the converse of angles in the same segment. Now this example looks longer, but it's actually the same amount. Because we need to find angle. That's one step. That's considered as one step. And then the next step, that's my final argument. Okay? So that's the second example. Example 22. This looks much more complicated. It has two circles. So we have two circles. They intersect at point A and B. We also have that these three lines are equal. AB, AD, and AC are equal. The rest are all straight lines. For example, CAD is a straight line. CB is a straight line. EGD is a straight line. And BFD is a straight line. Now, how about this? This point is not named. So perhaps we don't need to consider that point. Unless you think you need. But here, I don't think we need. Let's prove. First, B, E, G, F are concyclic. B, E, G, F are concyclic. Again, we have three ways. I'm going to use the second test. The second test is exterior angle and interior opposite angle. Now here I'm going to consider this angle and this angle. This angle is exterior. This angle is interior opposite. Let's find out if they're equal. Okay? A. Now look at the smaller circle, AFBC. In AFBC, the smaller circle AFBC, angle CFB equal angle CAB. Angles in the same segment. These two are equal. And then look at the bigger circle. In ADEB, the bigger circle, angle CAB equal angle BEG. These two are equal. Because exterior angle cyclical. So they're equal. So in the end, the three angles are all equal. So I have my final argument. Because angle BEG equal angle CAB equal angle CFB, therefore BEGF are concyclic. And I quote test 2. Exterior angle equal interior opposite angle. Now pay attention, these two are not the same. They are converse of each other, so pay attention to their reference. So that's the first part. Second part, let's prove that CGE is a right angle. This angle, CGE is a right angle. How do I know? Now, I already proved BEGF are concyclic. So if this is a right angle, then this one is also a right angle. So instead of going directly to CGE, I want to look at angle CBD. Okay, now why do I want to look at this angle? This is because I found something very special about the equal lines. So B. So you know that in the triangle ABD, not ABD, CBD, in this triangle CBD, it's very strange that AC equal AB equal AD, don't you think so? Now usually in a triangle you wouldn't find something that special when you have the A is basically the midpoint, which makes AB the median of the triangle. And the median of the triangle is equal to exactly a half of the line CD. That's very strange. That makes me think maybe this triangle is a right angle triangle, and it's not that difficult to prove. It's not that difficult to prove. I will say that because AC equal AB equal AD, right? These three lines are equal. Therefore, A is the circumcenter of triangle CBD. Now think about it. So AC can be radius, AB can be radius, AD can be radius. So if I have a circle at A and radius of AC, basically my circle at A will pass through CBD, which makes it the circumcircle of CBD. That means A is the circumcenter. I know we didn't go the traditional way, prove that, the circumcenter is the intersection of the perpendicular bisectors, but I hope you can understand that the circumcenter is also the center of the circumcircle. So if I can find a circle passing through C, B, and D at the same time and centered at A, then I can say A is the circumcenter. I hope that is a valid argument to you. Try to understand that. Okay, now why I want to do that? Because I want to say that angle CBD is right angle. Now how do I say that? Now because CAD is a straight line, that means CD is the diameter of circle CBD. Therefore, angle CBD equal 90 degrees. This is angle in the semicircle. Now this one is a little bit abstract because you must imagine there's a circle passing through CBD and center at A. Just that. Then you get 90 degrees. And the rest is simple. The rest is simple. In circle BEGF, we have angle CBD equal angle CGE, exterior angle cyclic quad. Therefore, angle CGE is a right angle. The proof is complete. Okay, now this part is a bit longer, but again, once you can dissect the whole proof into two parts, then you know it's just two parts. One part is to prove this is a right angle triangle, and the other part is these two angles are equal. Okay, last part. F is the orthocenter. F is the orthocenter. We already proved 90 degrees. Right? We already proved 90 degrees. I think this is 90 degree. We only need another 90 degree, which is this one. Is this 90 degree? I think already proven, right? Already proven. So let me write it down. C. Because CG perpendicular to DE proven in B. Also at the same time, DB perpendicular to CE also proven in B. So I have two perpendiculars. Now, technically there are three perpendiculars, but two will make the intersection. So we can draw the conclusion. Therefore, F is the isocenter of triangle. Let me write down CDE. The last one is actually effortless. If you do the part B very well, then the last part is not that hard. You know the definition and use the definition, that's all. Okay, so this is a relatively long proof. If you are aiming at the last proof, the last conclusion directly, maybe it's hard, but to build up from A and B, then it seems natural. Now you can pause the video and try the classwork yourself. Okay, and then you can look at my answer later. So this question. To prove that PQRS is cyclic quadrilateral, I'm going to use test 3, converse of angle in the same segment. How do I do that? This is what I do. This is what I do. This angle and this angle are equal. Because BQ is tangent at Q, therefore angle PQS equal angle QRT. Angle in the alternate segment. One segment, the other segment. You see, this is one segment, the other segment. These two are equal. And then these two. No, these two. The two next to each other. Now because QT equal TU, therefore angle QRT equal angle TRU. Now here I'm using equal chord, equal angles. Equal chord, equal angles. Equal chords, equal angles. And now I have equal angles now. Now because angle PQS equal angle QRT equal angle TRU, therefore PQRS is a cyclic quadrilateral. Test 3, converse of angle in the same segment. Okay, so equal angles. This one and this one. And use this one, the one next to it, as the link. Now, next part, proof angle triangle PQS is an isosceles triangle. PQS isosceles. Okay, I'm still going for the angles. Equal, equal, equal. Now we just need this equal. How do I do that? Use the circle. Use the circle. In circle PQRS, we have angle PSQ and angle PRQ. angles in the same segment are equal. And we already know angle PRQ and angle PQS are equal. Proven. Then we have equal angles. PSQ equal angle PRQ equal angle PQS. Since they are equal angles, I can say their sides are equal. PQ equal PS. Sides opposite equal angles. Now this reference is a long time ago. You learned in S3, S2 actually. You may want to revise that. Equal angles and then equal sides. And then you can say, oh, triangle PQS is an isosceles triangle. And then you're done. Last part. If ST equal SU, prove I is the incenter. ST equal SU. ST equal SU. Prove I is the incenter. Now, so far I have proven a lot of equal angles now, so I want to name them. Name the equal angles I have found. Obviously, I have new equal angles now, but the previous day I found full equal angle. I want to name them. So I name them X, 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 and X. Okay? I name them that. So, part C, I will let angle PQS, angle PSQ, angle SRT, and angle QRT, or X. Okay? Now, since these two are equal, so TR is already the angle bisector. That's one angle bisector. I can write it there, but maybe I'll write it later. The other thing is that it's not just one angle bisector. I must also say, oh, this is also angle bisector. Here, this is also angle bisector. Now, how do I do that? I will find these two angles. Okay? How do I find them? First, this one. This one. QTU. I can say because angle TQU, angle TQU equal angle TRU. Angles in the same segment. So this is X. There we go. I found. And then this angle, I also want to find this angle is X. And how do I do that? It seems like I don't have anything else to move on, except the newly added condition, TS equal US. TS equal US. So I have, because TS equal US, therefore angle STU equal angle SUT. They are equal. And we know that these are exterior angles, so this angle equal this angle. Then maybe I use another color so you can see. This angle equal this angle. And maybe I use this color. This angle equal this angle. So I have, because angle STU equal angle SRQ, this is exterior angle cyclical. So STU is 2x. So this is 2x. That means SUT is also 2s. Therefore, angle SUT is equal to angle STU is equal to 2x. This is also 2x. And we know this one and this one are equal. And since angle SUT equal angle SQR, exterior angle cyclic, then angle SQR also equal to x. So if this is 2x and this is x, that means this one is x. Therefore, angle UQR is also x. Let's write the final conclusion. The final conclusion. Because now angle QU and line TR are the angle bisectors of angle SQR and angle SRQ, and therefore I is the incenter of triangle SQR. Now here, similar to the example, we didn't prove OI is the intersection of 3 angle bisectors. We only use 2, and that is allowed. That's all. Okay, the last part is a little bit longer, but still, it's worth it. Ultimately, we're just going to find all the angles are equal. And these, of course, that they are all equal because this newly added condition ST equal SU. Otherwise, I can never find their equal angles. Okay? Next example. There is just one circle here, but unfortunately, you have this H and G are orthocenter and circumcenter of ABC. Now first, let's understand orthocenter. Now, if ABC is here, right? What does orthocenter mean? Orthocenter means that BH is perpendicular to AC, CH is perpendicular to AB, and AH is perpendicular to BC. I think that's what it means. Although that I haven't drawn the whole 3 altitudes. I didn't extend them. I don't have to. I know that they're perpendicular, even though they're not intersecting now. But the perpendicular relation still exists. That's how to understand orthocenter. Now, how about the circumcenter? Circumcenter of ABC. How do I understand that? Directly, you would say that G lies on the perpendicular bisector of AB, which is not shown here. G lies on the perpendicular bisector of BC, which is shown here because this is the perpendicular bisector. And G lies on the perpendicular bisector of AC, which is shown here. Perpendicular bisector. Right? That is one way to understand it. Also, as the circumcenter is the center of the circumcircle, now since the circumcircle is given, it's not said directly in the contest, but it's given. You can see that. The blue circle is passing through ABC, right? That's the circumcircle, and G is the center, basically. It's very subtle. It's very subtle. It says this is the diameter, it says the orthocenter and the circumcenter. It doesn't say directly that G is the center of the circle, but you should get that. Okay? Now AH is produced. That means this is a straight line AHE. And perpendicular from G to BC at F, perpendicular, and proof. Okay? How do I prove AHCD is the parallelogram? As you remember, we have 5 tests for parallelograms, and there is an extra one. Oh, just 5 one. I think 5 tests, including the definition. And here we're going to use the definition of parallelogram. Parallel. It's not that difficult. Because H is the orthocenter of triangle ABC, therefore AH is perpendicular to BC. They're not they are intersecting, but it's perpendicular. That's what it means. Perpendicular. This is 90-degree base. AH is perpendicular to BC. And also, because BD is the diameter of circle ABCD, therefore CD is also perpendicular to BC. I think that's enough to say they're parallel. Therefore AH is parallel to CD. Or you can say, oh, the corresponding angles are equal, but that's not necessary. No, it's not necessary. I think it's enough to just present that. Okay. Now there is another pair of parallel that is CH and AD, and it's similar. It's similar because this is perpendicular and perpendicular. So you can say similarly, CH is it's parallel, not perpendicular, parallel to AD as well. Therefore, AHCD is a parallelogram. And since we're using the definition, no reference is needed. That's part A. Okay. Part B. Part B, AH is 6 cm. How do you find GF? It's not that difficult. It's not that difficult. AH is 6, CD is also 6. Right? And GF looks like it's half of it. How do I know it's half? You see, this. Okay. I'll present it like nicely. So because AHCD is a parallelogram, therefore AH equals CD, opposite sides of parallelogram. CD equals 6 cm. Okay. Second, in triangle CDB, because G is the midpoint of BD, again, I'm using it's the center. G is the center, so I'm just using it directly. I'm not even mentioning how I get it. It's technically you can mention why you think G is the midpoint, but I think you can skip that. Can skip. And how about F? Is F also the midpoint? I think so. I think so. Because GF is perpendicular to BC, therefore F is the midpoint of BC. Perpendicular from center to chord bisects chord. Therefore, GF is equal to 1/2 of CD. This one is old. Midpoint theorem in a triangle. Therefore, GF equals 3 cm. That's all. That's all. Obviously, geometry is not that simple. You can improve by practicing. That's all. Bye-bye.